Hello, wonderful people. Welcome to Cosmology Talks. Today we have results from Euclid. It's hard to believe that's actually true, but it's crazy exciting. We are now well and truly in the era of stage 4 cosmology. What's more, it's amazing how much science and data this collaboration has put out today, when this is technically not their first cosmology release, which is actually coming next year. In fact, today's results come from just 7 days of data taking and 63 square degrees of what will eventually be 14,000. And yet they've still produced 27 separate scientific papers using the data. So keep that in mind while watching the videos and just imagine the glorious future that awaits us. It's kind of astronomy Christmas as well, because we have 2 videos from Euclid today. In this video we have Guadalupe Cañas-Herrera, who is a research fellow at the European Space Agency, talking about the telescope and the collaboration's overall goals, as well as Hervé Aussel, a researcher at AIM in Paris-Saclay, giving an overview of the data that is being released. And in another video released today, we'll have 3 more Euclid scientists telling us about some amazing results from 3 key areas impacted by today's data release. So when you're done with this video, you should definitely go check that one out. Welcome, Guada and Hervé. Do you want to start by giving us a brief overview of Euclid?
Euclid is a European Space Agency-led mission under the mission program Cosmic Vision, a medium class, and actually has already been in operation for more than a year. Launched on the 1st of July of 2023, the objective of Euclid is to 3D map the universe, so building the largest galaxy catalog ever.
Yeah, wow, that's really exciting. Looking forward to all the results in the future, but also the results today. So Hervé, do you have a brief teaser of all of the results we'll be hearing about today?
Yeah, today we are making public ESA and the Euclid Consortium, the Q1 data release, which is something to whet a bit the appetite of people for the big data release to come next year. It's 63 square degree of the Euclid deep field plus 1 pointing on the dark field, and we'll try to explain what's all about this.
Great. Well, this is very exciting. Let's get into what Euclid is in greater detail and what it is and was trying to do.
Yeah, well, first of all, thank you so much for the invitation. I'm extraordinarily happy to be here to give you a brief overview about Euclid, what it is, and what are the current goals, and actually already anticipating what we are releasing today, which is our quick one data release. So Euclid is a cosmological mission. What does it mean? So if we go to the next slide, we can actually see that cosmologist has what we call the concordance model, so the standard cosmological model. This model is extremely successful. Only with really few parameters we are able to explain most of the observations that we have today. However, this model basically says that 95% of the universe is composed by mostly 2 substances that we don't know the nature of. So 70% of it is related with the concept of dark energy. So a mysterious substance that we basically do not understand, but that we believe it is the responsible of the accelerated expansion of the universe, a discovery that already took place at the end of the last century. 25% of the matter content is in the form of dark matter. And in this case, dark really means that it doesn't interact with light. So a type of matter that we lack our understanding about its nature, but it doesn't understand with photons. Only 5% is what we call ordinary matter or baryonic matter. So the ultimate objective of Euclid is to basically understand this accelerated expansion of the universe and to understand as well the nature of that matter. And how are we going to do that? So on the next slide, we can actually see what is the foundation of this standard cosmological model. To explain this accelerated expansion of the universe, we use a cosmological constant, so a constant in Einstein's theory of general relativity equations, to try to figure it out more in depth. What is the nature of dark energy? We basically assume that instead of having a cosmological constant that it is explaining the accelerated expansion of the universe, we parameterize. So we try to understand this substance by studying its equation of states. And this is basically how we bring up this famous dark energy equation of state parameter, W0, WA. This is the goal of Euclid.
Why the name Euclid? Like a lot of the cosmological and astronomy ones I'm used to have their abbreviations or acronyms and you know exactly what they mean. But so why is Euclid called Euclid? Obviously, this is a person's name, not an acronym. I mean, I assume it's not an acronym.
This is a very interesting question, and it's actually a question that I have for a really long time. I think it's important to put the Euclid mission in perspective with a historic point of view. So, as we have seen, Euclid has two instruments on board, and the reason is because once we would like to do weak lensing and galaxy clustering. Euclid is actually the joint of two proposed missions to the European Space Agency back in 2007. So that was Dune, that it was aiming to do weak lensing from space, and space that actually wanted to do spectroscopic galaxy clustering from space. The European Space Agency saw a very fantastic opportunity to actually do both with one single spacecraft. So this is how it asked back the scientific community to put together a proposal for two instruments and one spacecraft. Because at the end of the day, what the ultimate goal of these two missions was to study dark energy, so that's it, that accelerated expansion of our universe. To study the accelerated expansion of the universe through this cosmological constant, we have to rely on the theory of Albert Einstein's general relativity. So basically, this theory tells us that there is a relation between how gravity works and the geometry of our universe. Because in ultimate instance, they needed to come up with a different name, and we know that this is somehow related with the geometry of our universe. Who's best to actually make the relation than Euclid? And this is how the Euclid mission came to life. So with Euclid, we are collecting tons and tons of data to be able to put the best statistical constraints on these two parameters. And how are we going to do that? Well, on the next slide, if we actually know, or we assumed, a cosmological constant, we can trace back the history of our universe across cosmic time. So assuming some initial conditions that have later evolved to form the current large-scale structure of the universe that we have today following the law of gravity, we can basically put some constraints about the density matter composition of our universe, but also how this expansion has taken place across cosmic time. Most of the information that we have these days about our cosmological model comes from the observations of the cosmic microwave background. So this relic radiation that basically tell us how the universe was looking like when it was an infant. Now we are moving to what we call large-scale structure cosmology. So we are going to study this large-scale structure, this cosmic web, how our universe looks like at really large scales by creating a 3D map. So this is the goal of Euclid. If we go on the next slide, what you can actually see is that Euclid is targeting the last 10 billion years. So basically from redshift 0 up to redshift close to 3. Why are we with Euclid targeting to study the large scale structure of our universe between these two redshifts? Because we believe that it is at this time when the dark energy domination, so basically this accelerated expansion of the universe, is starting looking like. Now, the question is, we have two substances that we basically pretty much know nothing about and that we cannot directly detect. So we observe the effects of dark matter by how it behaves according to gravity, or what is its effects in other the structures that we can observe. And dark energy we also observed indirectly its effects on how the universe is actually expanding. So with Euclid, we construct this catalog by measuring positions, 2D positions, shapes, and distances to billions of galaxies. And combining this information, we can construct what we call cosmological observables. So probes that contains information about that cosmological model, so that indirectly we can put constraints on dark energy and dark matter. And in the case of Euclid, we have two main primary probes, cosmological probes. The first one is cosmic shear. And what is the effects of cosmic shear? It can actually be seen in this video. So basically, we know the light that it is coming from very far away galaxies, basically its trajectory gets distorted due to the fact that we have tons of matter between those galaxies and us. Very similar to what it is happening with this penny in this bathtub. You know that there is something between the penny and us because you can actually see how the apparent shape of this penny gets distorted. Now, with just one penny, you don't get to actually understand how much, in this case, water is in the bathtub. But now imagine that you will have like a lot of pennies. You could actually actually constrain how much water you will have. And this is the case of what we do with cosmic shear. So cosmic shear, on the next slide, we can actually see that it has different regimes. So based on how we are located with respect to those galaxies, light and us, we could see direct strong effects, so really deformation, beautiful deformations of those galaxies in the background. This is actually something that we touched today on this quick data release, but also on its weak regime. So basically, this apparent distortion in the galaxy shapes can only be studied with statistics. And this last regime is what we are going to use for cosmology. Now, as you remember, I told you as well that we are measuring distances to galaxies. And why we are going to do that? Well, on the next slide, we already have an intuition of what it is going on. We measure distances to galaxies because we would like to see galaxies at different times. So we know that nothing can go faster than the speed of light. So basically studying different distances is as studying galaxies at different time frames. By studying the galaxies, we can the galaxies distances, we can actually see, we can observe or measure this expansion rate in the universe. Now, on 2D, what we observed is that galaxies can potentially trace matter in a very similar way as if we, from the outside of the Earth, we take a picture of how Earth population might be distributed, we might associate that basically we have more people living on places where we have more light. This is partially correct, but if this is the assumption that we will make, we will basically introduce a bias because we already know that there is tons of people living in Africa or in South America that in this case they are not traced by light. This is why we say that galaxies are a biased tracer of matter because what they traced is baryonic matter. So now, combining the apparent distortions of the galaxy shapes tell us what is the matter distribution. Distances, we can measure a rate of the expansion of the universe. And by combining the 2D information, as we see on the next slide, we can basically break this degeneracy so that we can actually distinguish between the total amount of matter containing dark matter and baryonic matter. And this is basically the scope of Euclid. Combining weak lensing with this last probe galaxy clustering, we can constrain the underlying cosmological model and potentially combine or compare with different models that tell us a little bit more about the nature of dark energy and dark matter. How do we actually do that with Euclid? Well, in a really summarized way on the next slide, what we can see is the following. With Euclid, we take pictures. Then we classify what are galaxies, what are stars. We focused on the galaxies. As I said, measure 2D position, the shape, and the distance. And as we classify about the distance, we can construct this 3D map of the universe large-scale structure. And this 3D map is the ultimate scope of Euclid by the end of operations. So successfully launched on the 1st of July of 2023, Euclid has already been for more than a year in operation. After as well as successful periods of commissioning and performance verification, what we call the Euclid-wide survey started on the 14th of February last year, 2024. Since then, Euclid has been operating in a really special point in space called Lagrangian 2, where it shared its neighborhood together with other special missions such as Gaia or the James Webb Space Telescope.
Maybe most of the people in the target audience of the channel know what L2 is, but do you want to go into a little bit more detail about why it's useful for space telescopes? Why are JWST, Euclid, Gaia all hanging out? I think Planck back in the day, why do they all hang out at this one point in space?
Yeah, so Lagrangian point 2 is a very suitable place in our very near space to operate this kind of space missions. And fundamentally, there are two reasons why. The first one is because with Euclid and as other, for instance, telescopes such as James Webb, we are aiming to actually look at the deep space. So what that means is that we don't want to have any kind of contamination in front of us, so the sun should be placed behind. And this has a double purpose because basically we are not getting the sunlight contamination, but also is fooling solar power into our spacecrafts and instruments, which is what we actually need. Reason number two is that it is a point in which the Earth is always have access in terms of telecommunications, and therefore you can have contact with the spacecraft, with the different missions on an almost daily basis. So therefore you can always not only correct for the orbit, but also download all the fantastic data that we are collecting. In terms of a spacecraft, Euclid is a pretty rudimentary but yet extraordinary mission. As we see on the next slide, Euclid is composed by a 1.2 diameter telescope with a solar sun shield and the payload module. The size of Euclid, very, as you can see here, and when I had the opportunity to actually see it in person, is fairly big. Now, in the payload of Euclid, is where you have the joys of our science. So as we see in the next slide, those are the Euclid instruments. So remember, we are targeting 2D positions of galaxies, shapes of galaxies, and distances. So what does it mean? We need to measure distances, but we also need to take pictures of those galaxies. So basically, this is what the Euclid instruments do. Our VIS, visible imager, is the one in charge of producing high-resolution images, which is what we are using to measure the shapes of galaxies. Now, with our near-infrared spectrometer and photometer, NISP, we measured those distances to galaxies using photometry and spectroscopy. The Euclid instruments are installed within the payload module. And one of the joys of Euclid is that when we are aiming to see one part of on the space, as we see on the next slide, with the same light, gets splitted, and we get photometric and spectroscopy information together with our visible information. So basically it's taking like 2 times 1 information of the universe. This is how the instruments more in detail looks like on the next slide. So actually Euclid is responsible for bringing to space the largest CCD combination of cameras, that is our fantastic visible instrument, and as well our near-infrared detectors that in this case they were provided by one of our partners, NASA.
I find it fascinating that you've got kind of the weak lensing camera and the spectroscopic camera on, not just on the same instrument, but taking the exact same light. That seems super powerful and exciting. Off the top of my head, it's not clear what possibilities that opens up, but it feels like there must be lots. So yeah, what types of foregrounds or systematics that are otherwise unknown unknowns does this allow you to actually look at?
One of the benefits is that if we have a transient, then we have it both in the VIS and the near-infrared colors, and we can compare with ground-based data taken at a later stage or earlier. And one of the big limitations in the mission is the amount of gas that we have to point and repoint the telescope. So having a complete data set once at the same time was really a bonus when we were designing the mission.
Well, in this case as well, having the same observation, because we share the same focal plane in both visible, that is what we use with cosmic shear, and as well photometric and spectroscopy, but in particular photometry. This allow us to make like a single unique combination for the cosmological probe. So I was talking about galaxy clustering, cosmic shear. In reality, the cosmic shear probe is not only weak lensing. We actually do weak lensing, but also angular photometric galaxy clustering, so basically the 2D positions in space with the distance using photometry, and the cross combination between the two. Because we are using the same data, we actually do as well a joint calibration for the shear measurements of the photosees and the photometric redshifts, and this in principle would be more sensible in terms of doing cosmology later, because the uncertainties are somehow combined. So what are the scope? As I said multiple times, constructing the largest galaxy catalog ever. So that's it, constructing the Euclid-wide survey. We are targeting 1/3 of the sky. And why 1/3 of the sky? Is not that we are not ambitious. This 1/3 of the sky is approximately 14,000 square degrees. The rest of the part of this sky is basically contaminated with the light of our own galaxies. This is why we are targeting 1/3, because we are interested in understanding what it is happening on the deep space. But today is not about actually the Euclid-wide survey. Today we are talking about the deep fields of Euclid, and in particular a subset of data. So that's it. On the next slide, basically we are talking about the deep fields. So who is behind the scientific exploitation, but also the operation of the instruments of this ESA-led mission. That is the Euclid Consortium, a group of more than 3,000 scientists, like all across 14 different European countries, with contributors as well in the US, Canada, and Japan. So conclusions. What's next? So Euclid is designed to study the nature of dark energy and dark matter. And for that, there is no question whatsoever that we are building the largest catalog, galaxy catalog ever, using photometric and spectroscopic information. By the end of operation, we will have this Euclid-wide survey, and hopefully we could be able to say something about the nature of dark energy and dark matter. The first Euclid cosmological data release is scheduled for fall 2026. That's it. It will cover a little bit around 2,000 square degrees. So there is still a long way to go into those 14,000 square degrees. But today we will discuss the amazing legacy science that you get to do with slightly more than 50 square degrees. So yeah, thank you.
What is special about Euclid being in space? What does it allow us to do, or what does that remove that is important?
Well, Euclid is taking the lead as our next generation large-scale structure experiment that aims to use this information encoded in the large-scale structure to constrain the information about dark energy and dark matter. But that doesn't mean that these concepts of weak lensing and galaxy clustering cannot be performed with telescopes from the ground. The reason why Euclid went to space is because we rely on obtaining the best information possible on the matter distribution across cosmic time using weak lensing. And as I said before, weak lensing relies on measuring extremely well the apparent distortions on galaxy shapes. So if we want to remove whatever possible systematic effects, that is, how our instrument behaves, from the fact that we are operating from the ground Earth and we have the atmosphere in between, the best thing is actually go to space. And this is ultimately the reason why Euclid will be one of the most powerful instruments, well, one of the most powerful experiments to do weak lensing, or we hope we are already seeing it, from space, because we don't get to deal with the atmosphere, and therefore the measurement of the galaxy shapes are better.
So on this particular slide we have on the screen at the moment, you have this equation at the bottom, W of Z equals W naught plus WA times Z over 1 plus Z. One of the hottest things in cosmology at the moment, if not the hottest, maybe it's even replaced the Hubble tension, is the fact that your friends at the Dark Energy Spectroscopic Instrument, DESI, when you combine their data with supernovae and CMB, or arguably even just one of those two, DESI plus CMB or DESI plus supernovae, are seeing quite substantial evidence that W0 and WA are not what you expect in lambda CDM. You're saying you've got this cosmological data release in autumn of next year. Do you anticipate that data release will have competitive constraints on W0 and WA, so that we've now got this independent measurement of it, or perhaps worst case scenario, some sort of non-measurement of it, and then there's someone has systematics?
So the cosmological constraints or the statistical constraints that we expect on W0, WA will definitely be competitive with previous results of our direct competitors such as DESI. And what does it mean? That in principle, if DESI is highlighting already attention with respect to lambda CDMs or seeing values for W0, WA best fits that does not align statistically with the predictions of lambda CDM, Euclid should be at least be seeing some hints towards this as well on the first cosmological release. If that is not the case, that will be basically, well, the game of science, right? So we will figure it out.
Okay, cool. Well, we've got a lot to look forward to from Euclid, but at the moment you already have this Q1 data release. So Hervé, what can people already go and see in all of the papers released today?
Okay, so I'm going to tell you about what we are releasing in terms of data and products. And it's actually, you have to realize that it's only 7 days of data acquisition by Euclid.
Oh, wow. Okay. Wow.
That's already quite a world of new data. So we are going to reveal one pass of the Euclid deep field. So that's 63.1 square degree with V's, NISP, and X data. One of the important things in Euclid is that we have a third instrument. It's all the ground-based survey data that we are using for the ground-based photometry in order to be able to do photometric redshifts. So this 63.1 square degrees that will give a flavor of what the Euclid wide survey will enable over 14,000 and next October. I mean, October 2026, we'll be releasing 1900 square degree. We won't show any cosmology. We don't do PSF model yet and shape measurement for weak lensing. We are very actively working on it for DR1, and there are 7 technical papers describing the data processing, plus 27 scientific papers using the Q1 data. And then there is another bit, which is one pointing of the dark cloud, and I will get to this at the end.
When you say you're not doing PSF, do you want to just put PSF as point spread function? Is that right? And
yeah, the point spread function. So basically, the nerve of the war for doing weak lensing is to have a very accurate PSF model. With Euclid, we have very, very strong requirement, 10 to the minus 4 on the accuracy of the PSF model. And so we are still working on developing our model. And so basically, for Q1, we just want to give a flavor of what we can do, how good are the image, but we don't get into the shape measurements yet.
Okay, and the reason this point spread function is super important for weak lensing is, I guess, that the telescope itself will distort images by some tiny amount, and you don't want to mistake that for weak lensing.
Exactly. You want to have a very accurate PSF model so that you measure the shape very accurately and you don't bias your measurements. Any kind of bias, especially if there is some correlation of this bias in the image, will lead to a spurious signal. Okay, so the deep fields. There are 3 deep fields, EDF-N at the top left, the Fornax field, which is 10 square degree on the right, and then this stadium-like field, which we call the EDF South, and which is going to be one of the deep drilling field of Rubin. So that's also very important for us. The EDF-N is the cleanest field in terms of its sitting at the North Pole, at the ecliptic North Pole, and it's a very clean field without very little contaminant. The 2 other fields are a bit more contaminated in terms of galactic extinction, but it's not very heavy. The Fornax field, the EDFS, contains the famous Chandra Deep Field South, which is a field that has a lot of data from Hubble, a lot of redshifts. So it's a very rich field that will allow us to do cross calibration with other experiments. We have a field of 0.54 square degree with Euclid. One Euclid-wide survey pointing is 4 dithers, so that we can fill the gaps between the CCDs and have a continuous image. And what you can see here are the paving of each of the pointings that we do to map the EDF North on the left and the EDF South and the Fornax field on the right. And so you can also understand why we didn't put the EDF South at the southern ecliptic pole, because there you can see there is a Magellanic cloud, and that's not good for cosmology. You want to see really far away. So what are we going actually to provide is this 63.1 square degree of V's, NISP, and X data. So that's the V's calibrated frames, 4 long and 2 short per survey pointing, so 4 dithers and 2 short exposures. The near calibrated frames, that's 4 frames per survey pointing in each of the Y, G, and H band. And then what we do is that we stack all this data together. So we make a stack of all the V's frame, all the NISP frames, all the also ground-based frames with the same astrometry. Everything is registered together. That's what you call the MER stack. And one stack is 30 by 30 arc minute tile. On this, we're going to extract a catalog for which we're going to provide photometry and morphology of the source. And that's morphology when doing, for example, 30 feet to the isophote. It's not yet at the shear level of weak shear level of measurement. We then measure a photometric redshift catalog that gives us an estimate of the distance of the object, a classification, whether there are galaxies, QSO, stars, and then physical parameters for the galaxy, for example, stellar mass, star formation rate. Then don't forget that there are also spectra, so we provide a spectroscopic image that are calibrated, the 1D spectra, because all the 4 images are combined for each object into one 1D spectra, and then we extract a catalog with spectroscopic redshifts. So we are outputting 4.3 million redshifts and 30 million sources with photometric data.
When you say outputting that, is that like publicly now available, or?
Yeah, you can go to the Euclid Science Archive and you can download the image, browse through the catalogs, make spatial query on the catalogs with the usual tools from astronomer like AstroPy, etc.
So 4.3 million redshifts. What would that, if we went back in time, what was that the cutting edge? What experiment was the cutting edge that got 4 million redshifts?
Let me rephrase it. We are outputting 4.3 million spectra, out of which we are trying to measure a redshift, but we only measured maybe 1 or 2% of these can provide us accurate redshift. And I'll discuss this at the end because there are a lot of caveats coming with this data. All right, so the processing, I'm not going to go into lots of details, it's just to highlight that very important are the X data that we don't distribute as such because we use the reprocessing from our colleagues, but that we distribute in stacks when we register and recalibrate everything to Euclid. And then what you can see here are all the catalogs that we are outputting. We are outputting 7 papers explaining all the processing and giving detail, but just to give you some example. So this is the vis and near data. What you can see is that the number count of galaxies, extragalactic objects in these are perfectly in line with the expectation that we can derive from the cosmos field. So this is we are working well. We are getting the signal to noise that is expected for a wide-like survey, so this is good. You can see the look of the images, and honestly, looking at Euclid image when you are working in the mission, it's just amazing. I mean, you see beautiful galaxies everywhere. So this is an example of one of the cluster, Abel cluster, which is in the EDF North. And what you can see here is strong lensing. So you have the big CD, central CD galaxy, and you can see this nice arm, this nice giant arc, which is red because it's a source that is sitting at higher redshift. And also you can see some lens point sources or small sources at the bottom left of the cluster. So this is the type of this data, and you're getting this. This is 1 arc minute per 1 arc minute, so image. So that's 1/30th of the moon diameter, and you're going to get 63 square degrees of that. So that's really amazing in terms of image quality. Then this is the check of the depth, and indeed we are getting the image depth that we were expecting. So what you can see here is that as a function of the wavelengths, all the bands that we are using, and indeed we are supposed to work at 24 with NISP, and we are getting this 24 magnitude, and we are supposed to be at 24.5 10 sigma for extended object, and you can see that this is even going deeper than that. So it's really nice, and you can also look at the green, red, and blue points and black points, which are the depth data, the optical depth data that we are using and that we are mixing with the data so that we can do accurate photometric redshift. I mean, the V band is really large. It's basically RIZ band, you know, when you compare to ground-based data. And so we absolutely need this ground-based data to separate and be able to get better photometric redshift. So in the south, we are using DES, the dark energy survey. In the north, we are using unions, which is a combination of Canada-France observation with megacam in U and R band, and hyper-supreme cam in G and Z band, and Pan-STAR in I band. So we derive photometric redshift, and here you can see a comparison on some of the fields, because these are fields that are already known, so there are already some existing redshifts, and you can see that in terms of photometric redshift, we are not doing too bad. It's not the best photometric redshift in the world in terms of accuracy. Why? Because we are only having in the south 4 bands, and in the north 5 bands. So the more bands, the better. But for Euclid, what is really important is not that we get super accurate photometric redshift, is that the mean ensemble is super well constrained, and that's a very tight constraint. And on this, we are going to, we know that we are really on track to get this very good constraint and photometric stability. So these are our good news. Then if you come down to the next slide, we are doing a classification using the photometry. And here you can see that A comparison of the blue point are the galaxies that we are measured compared to, for example, the cosmos observations, and same thing for the stars. And you can see that there are some variation from field to field, but ballpark, we are doing okay. And we are doing okay down to the magnitude limit where we are expected to work. It's 24.5, which is at the end of this straight line. So this is good. This is the slide that excites me the most in this data set. That's a physical parameter. So what you can see on the left is a plot as a function of the redshift of the specific star formation rate of galaxies that are measured in the field. Specific star formation rate, that's the star formation rate divided by the stellar mass. That's how fast are your galaxy evolving and changing. And what you can see on the right are histogram of the frequency of the data for different beams sample, comparing the data that we have and Cosmos. So this tells us we are doing a good job. We are measuring things as we thought they were. But then you need to think about it. Cosmos was 2 square degrees, a few 100,000 objects. Q1 is 63 square degrees. We are going to 30 million objects in these plots. That's really a super sample where you can, basically, you have redshift and log SFR, but then you can take any kind of variable and still find yourself with a sample that will be with tens of thousands of sources. So you can really look at fine effects in galaxy evolution, and that's a great. And then if you think about it, the R1 will be even one step, the same data, the same processing, the same information, but on almost 2000 square degrees. So that's going to be a game changer in the field. Okay, so let's go now to the hard point, which is spectroscopy. So spectra in Euclid, we don't have slits. I mean, if you take spectra observed with SDSS, we were putting a fiber on the objects that we wanted to observe. DESI, you have slits, and that allows you to only capture the light from the object you want to measure the redshift of. In NISP, we don't have slits, we don't have possibility. So you get all the spectra all at once. And that's what you see in the top right image here. You can see all these horizontal lines are spectra, and they are all overlapping and falling on top of each other. And the spectra of the object that is outlined in green on the left, at the very center of the left image, which is a H-band image, is the one that is circled in the blow-up that you can see. And it's actually a galaxy at redshift 1.6, and you can sort of make out the continuum and also make out the line at between 400 and 500. You can see a brighter dot, which is probably the H-alpha line. But then what you can see also is that there is a lot of crap there. There are a lot of other spectra. You can see also that you have these tilted lines that you see on the side. These are remnants from the previous observation where the grism was slightly rotated. So basically, there are then cosmic rays. So what we need to do is to extract a redshift from this type of data. And that's not easy.
And so the difference with something like SDSS or DESI is that, yeah, they know that the spectra came from that precise galaxy, whereas here you can infer it, but you don't know for sure. And obviously, you've shown us one image, and we as human beings can look at this and say, oh, yeah, I'm pretty sure that was the right one, and probably get it right 99% of the time. But the problem is when you've got 4 million galaxies, you don't have that kind of like, you need an algorithm to work it out.
Exactly. And so we know very well how to map one position in the image to where the spectra should be. But then you will have overlapping spectra that will fall on your spectra, and you need to disentangle everything. This is why we are doing observation with a different orientation of the grism. And so that what you see here are 4 images corresponding to the 4 dithers, where we tilt a little bit the grism so that we can try to get different orientation so that the contamination of the spectra will not be exactly the same. And so in the end, you combine everything and you get this nice 1D spectrum. And this is really a nice example with a magnificent H-alpha line that you see around the pixel 400, which tells us that the redshift is 1.63. And with confirmation, we can see some oxygen-free lines in the blue part of the spectrum to the left. But you can see that already they are much more noisy. And we are going to work at reasonably low signal-to-noise, 3.5. So this is a high signal-to-noise spectra.
Yeah, I was going to say, like, the 400 line here is not a good example because you can see it in all the individual things. But the one at 100, I feel like, is quite a good example, perhaps, because the black line looks very clear, whereas the other colors, maybe it's not so obvious that there's a line there, whereas in the black line, it's obvious there is a spectral line there. So that's a pretty good example.
This is a comparison of the DAISY spectra in HGF in the in the Euclid field south with so that's with our Euclid redshift, and you can see that we agree sometimes, a lot of the time, let's say, for the high quality measurement, but we also disagree for a lot of time, and so this is because Euclid spectra measurements are mostly failing, and you have to be really careful into using redshift. And we recommend that we check if you use a redshift that is not with a probability of being 99.99999% of being accurate, you'd better take a look at the spectra and check that it doesn't look like something fishy happened.
If I can just try and interpret this plot. So if the Euclid and DAISY spectra were all matching, you'd obviously get like a line that goes through X equals Y, yeah. And if it's not, you expect some scatter around that. There's some interesting features where there are other lines. Like, what is the physics that's causing like these?
For example, it's we consider as H alpha a line that DAISY consider as being oxygen free, or H beta or oxygen 2, a different line. And on this, it's not completely clear whether it's DAISY that is right or it's us that is right, because one question is we only have one line. And galaxy can have plenty of emitting line, and sometimes there are some redshift range where you can only have one line. It's either H alpha or oxygen 2 or Lyman alpha for the super high redshift. Then you have to compare to your ground-based photometry and try to infer whether your photometric redshift agrees with your spectroscopic redshift, which is something that we don't do yet, and that DAISY is probably doing. So this is part of the differences that can explain these spurious lines that appear in this plot. Okay, so the last target that we have in our sample is the dark cloud, and that's Lin Dark Nebulae 1641 in Orion A. And if you know Orion A, it's in the galactic plane. It's somewhere where you don't do cosmology, and there is a good reason for that, because look at the image. There are cirrus everywhere, dust lane, a young stellar object. It's actually really pretty. And if you go to the next image, this is a blow-up of one small bit of this, and you can see young stellar objects in the center with jets that are exciting the interstellar medium, and these are really brand new objects. But that's really not what Euclid is supposed to observe. So why did we look at this? Well, we had some issue. We may remember that we had some issue during the commissioning with the pointing of Euclid. And we had to do some tests of our fine guidance sensor. And in order to do that, we looked for a place where there would be very little number of stars. And so that we could really shake a little bit the system and try to see if we could point also where there were little. And so we went here. That's one of the places in the sky where you have least guiding stars available for Euclid. And so we observed for one day there, trying to get to shake our system and show that it was working. So as a result, we get these super nice images that are going to be great for our colleagues from Herschel. This is a star-forming region that was observed by Herschel, that has been observed by ALMA. But for us, when we are doing extragalactic work, well, this is a nice image. But we are outputting the level 2 vis and near products, so they are perfectly calibrated, and you can see that they are really having a great result. We don't produce photo-Z, spear, and SPE on this because there is nothing we can do with that. It's not extragalactic, it's really something else. And I caution you on using the MER product because MER, when we do the merge and the stack, we automatically subtract a background from every object, and so basically it's gonna have a weird effect on the objects that are in this image.
Away from the center of the galaxy, presumably there is still some dust and stuff because we're in the galaxy, right? We can't look from outside the galaxy. So is it possible that by looking at images like this, where there's lots of dust, you can kind of model the dust better to then better understand the more spurious dust that you're looking through when you look away from the center of the galaxy?
Yes, so absolutely. Although these are different, different type of dust. What you're seeing here are molecular clouds. So really a region of the sky where you have a high density. When I say high, it's a few hundreds atoms per cubic centimeter, which is high density for this type of things. When we are going to look at higher latitude, and we selected what we call the extragalactic sky. Guada talked about these 14,000 square degrees that are really outside of the plane of the galaxy, and we are really avoiding any kind of molecular cloud region. But you will find what we call galactic cirrus. So galactic cirrus are really look like cirrus. They are way thinner structure. So for example, one famous one is the Vela veil. It's a remnant of supernova that extend over many degrees on the sky. And this dust is much less, it still has an effect. So we need to characterize it, and we need to know how it's redden or fluxes, because otherwise it's going to distort our photometric redshift. So we need to take it into account. But they are not as extreme as these sight lines that we are seeing here. So it's you can still see galaxy behind, except that they will be slightly redden. Here, all the objects that you see are stars that are in the foreground. You don't see anything behind this cloud. Okay, so I would like to finish this by some really important caveats. I mean, Q1 is our first data release. The data processing is not yet fully mature, and it will improve a lot for the subsequent release. I'm currently working on preparing we're going to start soon the launch of the DR1 reprocessing, because it takes us 2 to 3 months to reprocess 1 year of data. So we already made some strong improvement. One of the things that you will see also is that there are some homogeneity in the X data. They are not in the original data from the survey. We had some bug that we discovered after the fact into the processing of the data. These bugs will be fixed into DR1, but if you see that some of the ground-based data that we are using, you see that there are some things that looks a bit fishy. It's probably coming from our processing and not from the original survey data. Another important caveat are the spectroscopy. So I told you that we are extracting all the spectra from every object that is brighter than 22.5. So that's 4.3 million spectra. Now, if you take what we are expecting as the number of objects that we should be seeing with H alpha in the range of that we can see, we are expecting roughly 100,000 sources. That's about 2.5%. So, which means that the sample that Euclid is going to study using this BAO is only 2.5% of all the spectra that we are extracting. For the other spectra, there are a few other galaxies which have other lines that are available to be detected. There are a few stars on which we can have enough continuums that we can determine what is their spectral type. But the vast majority of spectra, you cannot extract a reliable redshift from it. There is a redshift in the catalogs, they are flagged with low reliability, but there is a redshift in the catalog. So please use only highly reliable measurements and check the 1D spectra, and just don't blindly use the redshifts from the catalogs. Finishing the word of caution, the pipeline, ground segment pipeline is optimized for shape measurement of small galaxies. I'm talking about things that are 2 to 5 to 10 arcseconds across. So the low surface brightness features, like these nice clouds that we were seeing, will not be preserved by the science ground segment pipeline. Same if you're looking at tidal tail of very nearby galaxies, where you see galaxies encountering and then the interaction creates these very beautiful tails. It's very likely that we are going to take them out, but they are in the original viz and near data. So we have data processing and we have people in the Euclid consortium that know how to preserve this and use them for their own science, and that with software that will be around the year one probably provided. But this is not the goal of Euclid, that really wants to look for the small galaxies that are very far away. And then let me finish with this is not a caveat, but no weak lensing shear measurement. And in year one in October 2026 will contain the weak lensing shear measurements, also many other things, and on 2000 square degree. Just one thing to keep in mind here, and why we are a bit still excited that it's only 63.1 square degree, etc. I mean, if you think about it, this is delivering us imaging with a resolution of 0.18 arcsecond. It's very close to from HST. HST is 0.1 arcsecond. 63 square degrees, 7 days of Euclid observation, that's probably half the entire sky that was observed by HST. I don't have the exact number, but if you put everything up together, maximum it's 300 square degree. It's probably less because HST reobserved plenty of times the same target. So just think about it. This is really something that we are really excited about. The SGS delivers image and spectra, but also catalog with a high level of information. And Year 1 will cover 2000 square degree almost, improved processing, PSF model, shear measurement, cluster catalogs, weak lensing and galaxy clustering, cosmological measurement. So please stay tuned. And I will leave you with the list of the 7 technical papers that explain everything about what we do to the data.
I guess this is Cosmology Talks, and as you guys have stressed, this data release is perhaps not won't be anywhere near as useful as DR1 will be next year for cosmology. But do you still expect that in the next 6 months, lots and lots of astronomers and astrophysicists will be publishing many papers based on this?
When Euclid was adopted, it was a mission to do cosmology, but legacy science was very important for it. In terms of legacy science, here in the deep field, we are submitting 27 papers with very different type of science. There are people that are looking for dwarf galaxy close to the Milky Way in these fields, because we can see resolved stars of a dwarf galaxy with Euclid. There are people that are looking for strong lenses, that systematically looking for strong lenses, like I showed you on the Abel 2280. I mean, this one is super obvious. There are others that, if you remember, recently there was a paper by O'Riordan finding a strong lens around the nucleus of NGC galaxy, which is a very nearby galaxy. So that's typically the type of things that Euclid can do. There are a lot of papers looking at the evolution of galaxy and using the determination of stellar mass, star formation rate, using also classification, because, for example, when you have an active galaxy, active nuclei galaxy with an active nuclei, or a supermassive black hole, well, you will see your galaxy, but then you will see that the nucleus is really an additional point source on top of it, and this is great to see this. We have the near-infrared data, which is a great tracer of stellar mass. So the mass determination of Euclid are really excellent. This is really the beginning, and honestly, when I think of a project that I would like to do with this data, I need, you have 10 ideas coming, and then you have to decide for one, but it's really already something that is very, very exciting.
And you've called this the deep field. Is the 1900 square degrees going to be equally deep, or is this a particularly like you've looked deeper just in this now?
No, also that's maybe something that I need to come across, and that's a very good question. So this is the deep field that is observed like the wide survey. And during the course of the mission, we are going to observe 40 times to 53 times, depending on the field, these deep fields, and build up a sample that is 2 magnitude deeper than the wide survey that we will use for comparison, study systematics, look at effect at on the noise. Also, we are using this data because the fields are placed near the ecliptic. The field of Euclid rotates when it visits them, which means that the orientation of the GRISM observation will rotate. And so we are going to build a lot of different orientation, and this will help us to make samples which are really pure in terms of spectroscopy. That will help us to also check how are we doing when we do one pass of the field. So this is really, for us, these are really calibration fields that are going to give a sample that is going to be 2 magnitude deeper. I have a lot of colleagues that are going to look for very distant quasar in these fields, because going 2 magnitudes deeper, we should be able to get quasar at redshift 7, 8, and maybe 9, because that's where the race is. And this is also something very exciting, but this will be at the end of the mission when we have accumulated the full 6 years of data.
Yeah. So it's kind of called deep field with a view to the future where it will be very deep.
And actually, what we did was to select the passes that we wanted to show you and to distribute to the community. And so we try to look to take the best passes out of the various possibilities. Let's not kid ourselves. I mean, sometimes we have problems. So there were some passes that where we were observing the fields when we had a solar eruption. And then what happens is that you get a super high rate of cosmic rays. You have protons. Your detector are just registering impact of particles and not photons. And this is unusable. So that's 2 or 3 passes that we had to scrap. But in the deep field north, we still had a good choice of 4 or 5 passes, and we took the one that was the cleanest, basically. But we already have in-house deeper observation, indeed, when we stack them with these 5 passes.
Thanks everyone for watching. If you want more Euclid, go watch the other video that was released today on active galactic nuclei, galaxy morphology, and strong lenses. It's crazy how many new lenses and AGNs these guys have already discovered, so you don't want to miss it. And thanks, Guada and Hervé, for the wonderful intro to Euclid and this Q1 data release.
Yeah, thank you so much for the invitation. It's been a pleasure to highlight what Euclid is currently offer and just give you a sneak peek of what it is yet to come.
Yeah, same here. Thank you very much for having us, and thank you for letting us, giving us the opportunity to show why we are excited about Euclid and what is going to come for cosmology.